I would also like to thank the organizers for inviting me and giving me the opportunity to present some of my recent results on time delays in correlated photoemission processes. So this session here is called attosecond physics. So attoseconds is the time scale of the electronic motion of valence electrons in atoms and molecules. So the orbit time of hydrogen, for example, is about 100 attoseconds. So what I'm going to talk today about is time-resolved photoemission. So in the simplest case, we just really ask the question of how long it takes an electron to escape in Einstein's photoelectric effect. And then further, we will also investigate how this ionization dynamics changes when we have more than one photon involved, also more than one electron. Now the question is, of course, how such time delays, if there are a proper physical observable, and how we can describe them in theory and also measure them in experiments. So in theory, phase information is always contained, so timing information is always contained in the phase of the wave packet, which is related to the Wigner delay. And in experiments, time delays can, for example, be measured by attosecond streaking or also by other pump probe setups and interferometric approaches. So let me give you a brief outline of today's talk. I will first give a brief theoretical introduction into the Wigner delay, and then talk a bit about how such time delays can be measured in experiment. Then I will further talk about time delays in atomic systems. Then we'll focus on two-photon double ionization in helium. And in the last part, I will give a brief outlook on another pump probe experiment like quantum beat spectroscopy, which is also able to retrieve dynamical information on ionization processes. So this work was done in collaboration with many people. So the part on time delays was done in collaboration with Joachim Burgdorfer and Stefan Nagele from the Vienna University of Technology. And the last part was done from a current postdoc at the Louisiana State University in a group of Ken Schäfer and Matt Garda, and with experimental support from the group of Giuseppe Sansone in Milan, and many other people were involved as well. So the first question is if time in quantum physics is a proper quantum mechanical observable. So there has been a long ongoing debate in the last century about if time is really a quantum mechanical observable, so if there is a time operator, which technically does not exist since the energy spectrum is bounded from below. However, for scattering, so just for the positive energy continuum, there's something like a time delay operator, which was introduced in the 50s by Eisenwood, Wigner, and Smith. So let's talk a bit about this Eisenwood, Wigner, Smith time delay, what we understand with that. So it was first introduced for simple scattering process. So if you have just an initial wave packet that scatters at some potential surface, then we see that compared to a wave packet that has no scattering potential, it will arrive at some certain point in free space, delayed or advanced with respect to this freely evolving wave packet. And this is exactly what we call the Eisenwood-Wigner-Smith time delay, or short, just Wigner delay. So if we look at how this looks for the stationary scattering states, we have an incoming plane wave. We know that if that scatters at a potential, then when we potential free land here again, we just observe a scattering phase shift, and then within the stationary phase argument, we see that a wave packet consisting of such plane waves travels with the group velocity, and after it has scattered at some potential, it may be delayed or advanced by the Wigner delay. And this Wigner delay just results from this stationary phase argument from this scattering phase shift, so it's just the energy derivative of the scattering phase shift. Now for photoionization, the situation is a little bit different, since now we have an initial bound state and no incoming electron wave packet. So the incoming particle is a photon, which ionizes our electron, puts it in a continuum, and then, so this is what we call a half scattering process, and what we then, our time delay is then defined with respect to the incoming XLV pulse, with respect to the ionizing pulse. So if you look at that again in a picture of the wave packet motion, so as a function of time, here's the position of the electron wave packet. So initially it's bound, and then when the laser pulse, the XCV pulse arrives, it photoionizes it, and then at some point, if it's just a short-range potential and we have free space, it again travels just with the group velocity. But if we extrapolate back to the origin, we see that it is emitted as a time delayed or advanced. So this is what we call, what is our Eisenberg-Wigner-Smith time delay in this picture. Again, to remind you, so it's just the energy derivative of the scattering phase, or more generally for photoionization, it's the energy derivative of the argument of the transition matrix element. Or in a really general case, always the final wave packet, the phase information of the final wave packet contains also dynamical information. Let's come to the next part to see how such time shifts can be measured in probe experiments. So I will be mostly just only talking about attosecond streaking now. So let me explain how this works. So we start with a gas atom, then ionize it with an ultra-short XeV pump pulse. So we put the electron into the continuum with a certain kinetic energy. And then if we do that in the presence of a probing infrared field, then we see, depending on when we set the electron free, we gain a different energy shift in the end. So with this, we really just map the ionization time onto the momentum that we can measure, and that is our spectral information that we can measure. So really, if you now look at such a streaking spectrogram, which is the spectrum as a function of delay between IR field and XeV pulse, then we can, from that, retrieve time delays, and this is the spectrum of the pioneering experiment for photoionization in atomic systems, where in 2010, a delay of 21 attoseconds between ionization from 2s and 2p electrons in neon was measured, which triggered a lot of theoretical investigation, also in the meanwhile, more experiments. I want to mention that this is still, both in theory and experiment, very challenging, but we have gained a very good understanding up to now. So what I'm going to present is theoretical results. So we simulate such streaking experiments by solving the time-dependent Schrödinger equation for either just one electron in the external electromagnetic field. So we have the atomic Hamiltonian and the field interaction, either in length or in velocity gauge. If you want to do that ab initio, this is at most possible for two electrons, where we also have to take into account the electron-electron interaction. And so this can still be done with supercomputers. And then, if we, after solving the time-dependent Schrödinger equation in the external fields, we have our wave function. And from that, we can extract spectral information, which we then can compare to experiments, which is the same as spectrum we can measure experimentally. So let me show you an example of such a streaking spectrogram. Let's first just look at the, so it's just for Coulombic systems, for hydrogen here. So we really see that this, the momentum distribution follows the vector potential of the probing infrared field. And then if we look very closely, it's a little bit shifted in time, and this is exactly what is our extracted streaking time shift. And I also want to mention, so in theory, we can really compare to the vector potential, but in experiments, the IR field usually is not known. So in experiments, you always need two different traces that you can compare with each other. So you can only measure relative delays between two different ionization pathways. So now the question, of course, is we can now simulate or measure such streaking time shifts. The question is, what's the physical meaning of the streaking time shift? So in the simplest case, when we just have a short-range potential where the Wigner delay is well defined, we really get that streaking really equals the Wigner delay. Now, in atomic systems, we always have the long-range Coulomb potential. So we have no kind of free space, because the Coulomb potential, of course, is infinitely long-ranged. So if we look into that a bit more closely, so we have now the streaking delay in the dots as a function of final kinetic energy. And then if you look, so this is just for hydrogen. If you look at the Coulomb phase, then we have the short-ranged part scattering phase shift of the Coulomb phase, which of course we can take the energy derivative, which gives us this Coulomb Wigner delay, which is plotted up here, but this does not agree with the streaking simulation. So the problem is that we also have to take into account this logarithmically diverging part here, which we see that this gives a contribution, what we call Coulomb laser coupling, and this is just due to the fact that our probing infrared field just probes the our ionization process within a finite range. So we basically probe a bit of this logarithmically diverging part. You can also find an analytic expression for that. And this then gives perfect agreement with the streaking time shift. I'd also like to mention that this is similar to an alternative interferometric approach called RABBIT, which I think you will hear more about in the next talk. So here you also have this distribution into the, here it's called continuum delay, and the usual short-range linear delay. So this exactly gives the same information. So for Coulomb systems, you always have to take into account this Coulomb laser coupling. Now, if we go a step further, and we ask the question what happens if we have polarizable initial or final states, then actually this also shifts our continuum energy of our electrons and leads to another modification of the streaking time shift, but which we also know and can calculate. So we can still decompose the streaking time into these different parts. And this also holds true for multi-electron systems and also for molecules. And even if we have a really correlated process like shake-up ionization in helium, we can still decompose into these parts. But I don't have time to talk more about that, but want to advertise an article about attosecond chronoscopy, which we recently wrote for Review of Modern Physics, which should be coming out in the next weeks, hopefully. And I would also want to mention that Stefan Nagele has a poster tomorrow on time-resolved photoemission from interhedral 360. So it's even more complicated system, molecule, where we also try to find about the time delay, what happens if you have this C60 cage. So with that, I want to come to next part about two-photon double ionization in helium. So here it's a little more complicated, so now we really take into account the two electrons of the helium atom, and we ionize with an XeV pulse, but do two-photon double ionization. So we absorb two photons from the XeV pulse. And if the XeV pulse has a higher energy than higher energy than ATeV, basically, this process can happen sequentially, which means that really first one electron gets emitted and then the other electron. So if we, for that, look at the energy distribution, so this is the spectral distribution of energy E1 and E2. When we first look at the integrated version here, so we have this double peak structure for the sequential process, where we really can say this higher energetic peak here is due to the first electron emission, since the first ionization potential is lower, and the second peak here is due to the second electron. And of course, in principle, we have a six-dimensional wave function. So we have all the different directions and the two energies. And in the following, we just focus on back-to-back emission, which is the most probable case. So let's look now in a timing domain what we expect. So if we have an ionizing XeV pulse, like a Gaussian-shaped one, then if we would just absorb one photon from this pulse, then on average, this will be absorbed at the center of the pulse. So that is what usually defines our time zero for the photoionization delays. But now, if you want to absorb two photons from one single pulse, then just from a stochastic argument already, you see that these photons won't be absorbed at the same time, but there will be some time delay. So one will be absorbed earlier and the second later. So now the question is what we see if we do a streaking simulation in this case for these two photon events. So if you really see the time ordering and the time delay between those two photoemission events. So here we have again the energy distribution, and these are the two integrated versions. I just mentioned this lower energetic part is due to one photon double ionization, but I will not talk about that today, so just focus on the two sequential peaks here. We're now going to see a movie, what happens when we really perform this streaking. So we have a different delay between XeV and IR pulse, and this will be the streaking spectrogram here. So if you now, for example, look at just the integrated spectrum, we really see that this shifts according to the time where we are at the laser pulse. And so here the streaking spectrogram is recorded. But what we also see, because the time delay here is quite big, So this is really a pretty complicated motion because we have now two electrons that are both in the continuum and both get shifted by the IR field, but they are ionized at different times. So you really see a kind of funny motion here. And if you look closer at this streaking spectrogram, now we really see with bare eye that those two streaking curves are really shifted by a delay of a couple of hundred attoseconds, depending on the duration of the ionizing XeV pulse. And the other thing, what is really nice, what we see, we already know from the kinematic information that the higher energetic peak is due to the first electron emission and the lower energetic peak due to the second. But here, now for the first time, we can really see that in a time-resolved measurement. So we really, not only qualitatively, but really quantitatively measure the delay when those two ionization events happened. So, yeah, so this is really an example that time ordering for indistinguishable electrons becomes accessible by attosecond streaking. So in the beginning, I told about the Wiener delay. So we said that always the final wave function, so the phase information of the final wave function contains also information about the ionization dynamics. So we look at that here now. So this is again now a streaking spectrogram, and here we look at just the information of the wave packet without infrared field. So the spectrum again, and then this here, what's here plotted is the Wigner delay, so the energy derivative of the phase of our final wave packet. And here also we very nicely see, have this time resolution and really see what happens. If you look at this energy here, where we really have the high energetic peak, so the first one, this really gives us a negative delay or advance. This other peak is the second electron, which has a positive delay. And then also very interesting, if you look at equal energy sharing, so somewhere off the sequential peaks, then we see near zero delay. And it also completely makes sense since we know that if you want to have this, if the electrons should share the energy equally, then they have to be emitted within a short time range, and that is reflected here in this Wiener delay of the final wave function. So now let's compare. We have now the information from the wave packet, so the Wigner delay, and we also know we have the streaking time shift. So first here, and I plotted this here now as a function of pulse duration of the ionizing XeV pulse. So first what we see is this really scales linearly with the pulse duration, so the longer the ionizing pulse, the more time the electrons have to be emitted. Then it shows, so the green dots was the Wigner delay, the Azimuth-Wigner-Smith delay, and the red dots are our streaking results. And here what I also showed is this uncorrelated limit that we just expect from a stochastic event of absorption of two photons. And we see that streaking and Azimuth-Wigner-Smith time delay doesn't completely agree. But then again, if we take into account a contribution from this relative Coulomb laser coupling, and then we need actually another contribution because you saw that this streaking with the two electrons is quite complicated, so it's difficult to really extract the streaking delay from this streaking trace. So this gives us another contribution, but then we see, again, perfect agreement and can again explain the streaking delay in terms of the Wigner delay and these other two terms. Okay, with that, I would like to come to the last part of my talk, which is a little bit different than what I talked before. So now we look at the multiphoton quantum beat spectroscopy experiment, but also with that we'll see we are able to gain information about the ionization dynamics. So with that, now we use an interferometric approach, and it's a quite different regime now. So what we have, we look again at helium, but this time just single ionization. So in the first step, we start from the ground state and populate a bound wave packet below the ionization threshold with an XeV pulse. And then in the second step, we ionize with an rather short 7 femtosecond infrared pulse. So that this is just used to really put this bound wave packet into the continuum. And for that, we also do a pump probe scan. So this is always for times when the IR field arrives later than the XeV. So really in the first step, we just create this wave packet, then we let it evolve, And of course, the different bound states evolve with different energies, so that we see then in this final spectrogram as these beatings. And also advertise for the experimental realization of that. Maurizio Riduzzi from a group in Milan will have a poster tomorrow on coincident photoelectron spectroscopy with the reaction microscope. But I know in the remaining time of my talk, we'll just talk about theoretical results for this beating spectroscopy. So let's look again at this beating spectrogram here. So we have, as a function of delay between XUV and IR, we see these nice beatings. And now, as we heard already today, we can analyze that by Fourier transforming along each final photoelectron kinetic energy. So that's what we do now. So let's first look at this at the absolute value of this Fourier transform, where we nicely see all those peaks here, which are these beatings, which correspond. So for example, if you look at this first one here, this corresponds to the beating between the two pathways, between an initial 1s4p state plus an IR photon and the 5p plus 1 IR photon. And then, I think I forgot to mention before, let's go back. So the nice thing here, what we try to look at is just ionization with one photon, but we can also ionize with more IR photons. So here, from the 2p state, for example, we can get with 3 IR photons, get the same continuum energy. So this 3-photon process interferes with the 1-photon process. So this is what we see here for these higher energetic peaks, which are due to interference between 2p states and a 5p state here, for example. Another question is, we have this, not only the spectral information, but we also, again, of course, have phase information from this Fourier transform. So the question is now, what does this tell us? So it's here the phase of this Fourier transform. So from one part, of course, quantum beat spectroscopy is used to characterize the initial wave packet. But the problem is, in order to do that, we also have to understand the ionization process. So that's what I'm now going to focus on the last slide to look at. So we assumed here a flat initial phase, but now we really look at these different phases that we gain from just the ionization step by the IR field. So now we're going to look at just 2 examples at the phase now along the final kinetic energy. So basically it's just a difference phase between 2 ionization steps by the IR field. So for example, this first one, which was just the 1 plus 1 photon process, this is pretty flat here, but this is due to the fact that all the 1 photon phases, atomic phase and Coulomb, and so on, this cancels because we interfere 2 pathways at the same final kinetic energy. And all those phase information usually depends on the electron energy, so this cancels out. However, now if you look at the 3 plus 1 photon interference here, then we see that this has a slope. Now again, with the slope, we can calculate a Wigner-like delay from that, so take the energy derivative of the slope, and this corresponds to some time delay of here, about 750 attoseconds. So this is kind of an indication that this is, again, a sequential process. So it takes some time to absorb 3 photons. It takes more time to absorb 3 photons than just 1. And yeah, and then the last thing, we also, in order to see this 3-photon process, we have to use quite a high intensity. And if you go to a little even higher intensity for the IR field, we see this funny bending of this difference phases. And this actually we could identify this is due to depletion of the initial state, which also modifies the ionization dynamics. And if you're interested in more about that, I will also have a poster on Friday about this last part. And with that, I want to summarize my talk today. So I first introduced the theoretical background for photoionization time delays, and then showed you that streaking is able to really retrieve delay information, and it is decomposable into different parts, which we all understand. Then I showed you about two-photon double ionization in helium, where we really saw that time ordering really is a physical observable, which is accessible by experiments principle. And in the last part, I introduced this quantum beat spectroscopy setup also as a method to gain timing information or dynamical information. And with that, I would like to thank you for your introduction, for your attention, sorry.